about batch processing and when the jobs are coming in ascending order. When it comes to shortest job, first again, shorter job, if we have a control on that, then again, this is a good algorithm. Shortest remaining time, first again, if we know exactly the next CPU bus time for the next job beforehand, then again, this is another, good algorithm. But again, some if and buts are there. Priority scheduling has its own pros and cons. Round robin has its own pros and cons. We have to adequately select the quantum size. So we should avoid with the both extreme. Either it will become first in first out if the quantum size is big as the largest job, and if it is too small, then increased number of context switches will make it really unsuitable. So this means every as a conclusion that every algorithm that we have studied has its own pros and cons. Well, at the other hand, we see, for example, there are certain type of algorithms that for them, one type of technique would be suitable. So this means it's not something one size fits all. Yani, for example, one algorithm will be best for all type of jobs. It depends. For example, when we talk about round robin, it will be good for the interactive nature of jobs that need a small CPU time and repeatedly they need this time. So round robin could be a good approach. Similarly, for the jobs that are having priority. So priority scheduling could be another any approach for certain type of jobs. So the idea is why not we go for a mixed approach. In this way, we divide the huge ready queue. The ready queue is consisted of several processes, which is the main memory. A lot of processes are there that are waiting for the CPU time. What if we divide this one single long queue, one single long ready queue into a number of sub queues like multi queues, and in each queue we admit the jobs that are of a particular type, and then we employ the suitable most algorithm for that queue, and then we apply similar technique for the rest of the queue. So that's the idea of multi-level queuing. So then we are going to talk about it in the subsequent part, which is the second part. We will talk about multi-level queue scheduling. We will also talk about multi-level feedback queues, where, for example, the jobs can also go to and fro from one queue to another. Likewise, we'll be talking about thread scheduling, and then finally we talk about the algorithm evaluation parameters. So as I mentioned in the multi-level queue scheduling, so another class of scheduling algorithm has been created for situations in which processes are easily classified into different groups. So like, for example, we can have foreground processes, we can have background processes. The foreground processes are more interactive. They are GUI-based processes, graphical user interface processes. User interaction is more important. So this is foreground processes that are visible and we can interact with, like Explorer, like desktop.exe, and whatever that you can see in the foreground. On the other hand, when we talk about background processes, they are mostly the batch processes that start with a certain. Let's say when we boot up the computer, boot up the PC, and then there are certain tasks that are carried out. This is actually kind of batch processing. For example, boot up test, for example, CMOS test, BIOS test, and then we go for the initiation of operating system, and then certain tasks are done that is known as the batch processing. This is mostly done on the background, the daemon processes. So we can classify them first of all depending upon their nature. Then a multi-level queue scheduling algorithm partition the ready queue that I mentioned, that a lot of processes are in the one long ready queue. They can be further classified, further partitioned into several separate queues that will show subsequently. And each queue has its own scheduling algorithm. For instance, if we talk about these two type of these two type of jobs. So for example, we will prefer round robin for the foreground because they need more interactive, and repeatedly they need small CPU bus time again and again. So we can prefer for them. And for the background processes that are batch processes, we can easily, arrange them in an ascending order. So batch processing, so we can employ first come first serve for them. So have a look at it, for example. So we can create a different kind of type of processes. For example, we can schedule them like real-time processes, system processes, interactive and batch processes, and they can also be arranged in type of priority, because when we talk about real-time system, real-time processes, they need interaction in the real time, so they must be responded immediately. So they are having highest priority. Then system own processes, operating system own processes, they are having relatively high priority. Then we talk about the GUI based interactive processes, while the batch processes are at the lower side that run on the back end. So scheduling must be done between the queues. So fixed priority preemptive scheduling, first of all, we will talk about that serve all from the foreground, then from the background. So this may cause possible starvation if we schedule them that, for example, firstly handle all the high priority processes and then go for the low priority processes. This could one of the choice, but eventually it can end up in starvation. The other option is that we go for the time slice. So each queue gets a certain amount of CPU time, which it can then schedule among its processes. So this means we say, for example, let's say we are having four queues over here. So let's say we divide equally, for instance, the CPU time 25%, then that 25% time, then each queue can further divide this time among the processes it admitted. So usually we see, for example, that the foreground processes they need, for example, more time. So we give, for example, 80% of the CPU time to the foreground processes that need more CPU time, and they are employing the round robin. On the other hand, on contrary, we can give 20% for the background processes running the first come first serve. So this is one of the choices. Okay, so with priority scheduling, we have separated queues for each priority. So each queue has full priority over the lower level queue's priority as a upper level, which is guaranteed with the preemptive scheduling. So let's say we are having the processes with having the highest priority, like priority 0 with priority 1, and then eventually the priority n, which is the lowest priority accordingly. And here T's are representing the time slots that are given to each process. So you can see, for example, the time slot are given, for example, T0 to T4 are given to highest priority processes. Then priority 1 will be having from T5 to T7 time slot, and then, for example, T8 to T11, and likewise, for example, up to any nth. So the time can be divided accordingly in this way. What is takeaway from this slide that higher priority processes will get more time and earlier than the lower priority queues. All right, so when we talk about, so this is one type of the queues that is known as multi-level queues. In these queues, once the process admitted in one queue, it will be exited or terminated from the same queue. So it's not allowed to move one process to another queue. So this is one of the approaches. In the second approach, that is known as multi-level feedback queue, what happens? Let's say that with the passage of time, certain processes that they execute some of their time. Now their priority can be improved. Now, for example, their size can be reduced. For example, they are becoming shorter than their previous size, and so on and so forth. So with the passage of time, they may be now become more suitable for a higher priority queue, or for another type of queue. So what we can do in the multi-level feedback queue, that we allow the processes to go from lower priority to higher priority mainly. This means they will go for a promotion. It is less likely that, for example, the processes are sent from higher priority queue to the lower priority queue, but mostly it can be other way around. So a process can move between the various queues. The idea is to separate processes according to characteristics of the CPU burst with the passage of time. So if a process uses too much CPU time, it will be moved to lower priority queue. This scheme leaves IO bound and directive processes in the high priority queue relatively. Aging then can be implemented using multi-level feedback queue. A process that waits for too long in a lower priority queue can be then moved to a higher priority queue with the passage of time, so that we can prevent the starvation. So we can devise the mechanism, our operating system can devise the mechanism based on which the promotion or demotion can be done, depending upon the nature of the behavior of the process over the time. So multi-level feedback queue scheduler is defined by the following parameters. How many queues are there, first of all? Scheduling algorithm for each queue, which algorithm should be there for each queue. Accordingly, we will decide that which process will move from which queue to which queue. Method used to determine when to upgrade a process, when to promote a process. Similarly, when to downgrade a process, how to demote a process. So we should be having certain criteria to define them to move the processes from higher to low and lower to high queues. Method used to determine which queue a process will enter when that process needs service. So we also need to know that if the process goes for the waiting state, then which queue it will go eventually after the service. So as an instance, we can see here that we are having a 3-level multi-level queue with feedback. So Q naught, the first Q is having a round robin with quantum size 8 milliseconds. Q1 is having again a round robin with a quantum size 16 milliseconds, and then we talk about the first come first serve. So for instance, what's the idea behind it? That first of all, that the processes will be entered in the first queue, and in the first round they will get 8 milliseconds each. Now, either the process will finish the job if all the jobs that are having less than or equal to 8 milliseconds. Otherwise, they will go to 16 milliseconds. So it's very likely now that the processes that haven't finished in the previous queue, they will finish in the second queue because quantum size is relatively bigger. Now, again, the exit point will be here, and if from the second queue, they will be exit here. Again, if there is some leftover, then they will go to first come first serve. Now, by the time they reach to the first come first serve, already they have spent almost 24 milliseconds with the CPU. So now they become relatively smaller, which will become more suitable for the first come first serve scenario. All right, so this is how the things will be executing. So scheduling a new process enters queue not first of all, which is serving round robin. When it gains CPU, the process will receive 8 milliseconds the first time. If it does not finish in 8 milliseconds, it will go to Q1. Then it will get 16 additional milliseconds. Still, if it is not finished, then it will go to the third queue, which is first come, first serve. So this is an example. This is how the behavior of the multi-level queues can be potentially. All right, so likewise, we talk about the process scheduling. We also talk about the thread scheduling. So when threads are supported, thread scheduled accordingly, but not the processes. This means one process, one of the thread will be getting the CPU, and then there'll be a competition among the threads belong to each process. So distinction between user level and kernel level threads is very important because the kernel level threads are having higher priority than the user level threads. So for a system using many-to-one and many-to-many model that we have seen previously, so the thread library scheduled user level threads to run on the lightweight process because by definition threads are known as the lightweight processes. This scheme is known as process contention scope since competition for the CPU takes place among the threads belonging to the same process rather than the process among the processes actually. This is typically done by priority set by the programmer as far as the user level threads are concerned. When we talk about the kernel level thread to schedule onto a CPU, the kernel uses system contention scope, which is defined at a system level, at an operating system level, not at the end user level. So competition among all the threads in the system will be then taking place. However, the systems that are using one-to-one model, such as Windows, Linux, and Solaris, schedule thread by the system contents SCS, which is system-based contention scope. So this is how we can see, for example, the process scope. These are the unbound any threads, and these are the system scope for the bounded threads. And then we can see, for example, these are user level threads, and these are the kernel level threads, and these are the processes at the next level. So we know that for execution of the user level threads, obviously the kernel level threads are involved, and this is how they are scheduled. All right, so when we talk about evaluation of the algorithm, so there are different criteria we have seen previously. For example, average waiting time, average turnaround time, and similarly. So how to select CPU scheduling algorithm for an operating system. So determine the criteria, then evaluate the algorithm based on that criteria, and then we can compare them based upon the scenario given to us. So deterministic modeling, type of analytic evaluation, takes a particular predetermined workload and define the performance of each algorithm for that workload. So for example, in this example, we are given 5 processes with their own respective time, and we assume they are all arriving at time 0. And then we employ different kind of algorithm, and we see that which algorithm is ended up with the minimum average waiting time and minimum turnaround time. So for instance, when we talk about 3 algorithms over here, we talk about first come first serve with 28 millisecond in the average waiting time that we approach. When we talk about non-preemptive shortest job first, it ended up in 13 millisecond because the jobs were already there, they were in the batch, we can arrange them and then we execute them. When we talk about the round robin, so it ended up in 23 milliseconds. So this is how we can see that obviously in this context and in this scenario, shortest job first has outperformed while first come first serve was on the on the lower side. So that is something we already know, that when we are having multiple algorithms involved, and